Good afternoon, everyone. Welcome to this session. My name is Vincent. I'm the Chief Technology Officer for Red Hat, based in Asia Pacific. So I work out of Singapore, but I do spend a lot of time on the road, visiting, of course, our engineering offices here in India, in Bangalore and Pune, but also meeting with a lot of enterprise that are really trying to understand how to get into the artificial intelligence journey and to leverage cloud-native technologies. We've heard a lot about AI over the past couple of days, how exciting it is that AI is becoming cloud-native. I'm going to take a slightly different view in this session, which is to focus on one of the key challenges we see right now in AI adoption, which is sustainability. How to build a platform that caters for efficiency of resource management. And of course, behind this, you would all have in mind how difficult it is these days to get hold of a GPU. When you get hold to a GPU, you want to maximize the usage. So we are going to discuss some of the challenges as well as some of the work that is happening in the Cloud Native Computing Foundation across multiple projects to look at this type of challenge. I'm going to try to spend a bit of time explaining the topic itself, how we look at the value chain of AI with sustainability in mind. I'll share a bit as well about high-level architecture. How do you architect an AI platform for efficiency? And hopefully, we'll have enough time to cover a few examples of great technical work that is happening across a number of CNCF projects. So let's start a bit with a few market trends. So if you look today at AI, and you'll see in this graph here, I think I see often on the ground this mindset that somehow AI and Gen AI and this explosion started with ChatGPT. What I want to share with you is absolutely not. Since 2010, and essentially neural networks, we've seen an explosion of resource requirements due to AI workload. The inflection is quite clear. From there, and since 2010, we see an increase roughly 4 to 5 times a year in terms of resource utilization, specifically for AI workload. The reason is the way that we use AI technologies today is we need a lot of data. We need to do extensive distributed training across the stack for this very exciting but also very resource-intensive neural network that needs to be trained. And they don't need to be trained only one single time because data changes, so we need to do that repeatedly. The second aspect of this is, and it's a very interesting thought, I mentioned earlier, it's hard to get rid of GPU, to get hold of GPU, but there is one resource that has become even more difficult to get hold of and in demand is energy. A lot of data centers that we have, not just in our region, across the world, they've been built and the power management capability they have been built and planned for traditional workload. So what you will find is a lot of data centers out there, they have some agreement with power provider that do not cater for the explosion in power requirement that is necessary to feed the GPU with energy. This is a real problem. If you are interested in it, one of the best examples is now we have the United States rehabilitating nuclear energy just to be able to feed their AI requirement. There is no other reason. It's an economic reason. They need AI to happen. They need to own the AI revolution. So it's arms race to the ownership of AI. This cannot happen without power. Very important aspect. With all this excitement, of course, comes challenges, but also risk and regulations. So another key emerging trend we see is obviously emergence of green AI standard practices and regulations. I would like to mention the EU AI Act. So in Europe, if you look at regulation of AI, there is already a provision for provider of AI models and workload to be accountable for the amount of carbon emissions that they create. That is extremely important. Think about it. Most of these providers, do they even know how to measure their carbon emission end-to-end? This is a big problem. Last but not least, to finish with a bit of a positive note, AI obviously creates a challenge from a sustainability point of view, but it also creates opportunities. A lot of efficiency that we get today in power management, carbon emission, optimization, they can actually benefit from artificial intelligence to happen. Very simple example, power energy grid management. I work as well with telco providers very often. They are actually using AI model, predictive model, to optimize the way that they manage power allocation on their grid and in their substation. They actually need these kind of models to be able to do this at scale. It cannot be done with just human pretty much running AI ops manually. They are managing, predictive performance and capacity requirements, right? Where I think the opportunity is for our community, since we are engineers, is that today, obviously, people they want to get into AI, but these statistics you see there, 74%, this is actually the percentage of enterprise who say they are struggling today to orchestrate AI workload at scale. So I have a bit, and we had a keynote earlier on. I thought it was a bit too positive and optimistic, to be honest, when we saw a keynote saying, oh, Kubernetes and cloud native have solved AI. I totally disagree with this. The statistics shows it. Most enterprises that are trying to use AI and build AI infrastructure today, the majority is struggling to just scale distributed workload for tuning. I'm not even talking about complex use case, managed inference and so on. So this is still where we are on the ground in terms of AI usage. Optimizing AI for sustainability actually takes a very, very wide view of the sustainability chain. I won't cover everything. I just want to mention it. When we look at the problem, we start from energy infrastructure, access to power. Do we have data centers that have access to solar power, wind power, renewable? Being able to access renewable power is deeply important. PUE of your data center, type of hardware you are using, all play a major role in the total footprint. But what I'm going to cover today is the right part of the life cycle, which is the software and operation. Assuming you've got a data center, assuming you've got the GPUs, how do you maximize the use of your resources? And how do you get the most of the energy spent that you are going to make? And this happens obviously with proper orchestration, so usage of cloud-native technology, and it happens with proper SRE, platform engineering practices applied to artificial intelligence. So now, you're going to ask me, how is this relevant to the CNCF? So I just want to share with you some relatively recent efforts that have been happening. We all know the CNCF mission. We want to promote the use of cloud-native technology, standards around them. I think there is a big, we've seen again in yesterday's keynote, a lot of companies out there now have to deal with hybrid workloads. They run some workloads on the cloud, private data center. I've got a lot of customers as well now running Kubernetes on edge as well. AI workloads are the best hybrid workload you can think about. AI is hybrid by definition, because you will want to tune or train your model where your data is generated. And 90% of the time, where you generate the data is not where the model needs to be consumed. So that creates this situation that already as an engineer, I need to support organization to think about where do I keep the data? Where do I train the model? Where do I deploy the model? How do I maximize the efficiency of data transfer, networking, access to compute? There's a lot of hugely important design decisions that you need to think about from the day one you want to get into the AI journey at scale. So on the CNCF side, it's an interesting problem because it's a problem that is at the intersection of at least two types of work that we are already doing. On one hand, we have the tag runtime that created an AI working group. On the other hand, we have another tag, which I'm part of, which is the environmental sustainability tag, where we care about making cloud-native technology sustainable. We decided to collaborate between the two groups to build a white paper explaining best practice of AI system design in cloud-native environment. So we started this engagement about 3 months ago. Right now we have a draft paper, which we are extending to reviewer. We are trying to finalize the first version of this paper by end of Q1 next year, and it's going to contain a number of best practices around the management of AI. Won't go into the detail of the paper because it's already long, but we are approaching the problem from 4 dimensions. The first dimension is the deployment environment. Where do you deploy your AI system? Public cloud, private cloud, on-prem data center, near edge, far edge, edge device. A very wide diversity of environment deployment here. Type of AI system. Are you doing computer vision, large language model, small language model, predictive system? The type of system, the way you generate the data, the way you consume it, the need to retrain models frequently or not frequently, it will all play a role in your system design. So this is very important. AI lifecycle, optimizing AI for tuning and optimizing AI for inference is 2 hugely different problems. So if you solve your need to tune your own language model, like you have not solved all the challenges you will have doing widely distributed inference and scaling. Those are almost 2 different disciplines. And the last is persona, because when you operate AI at scale, obviously you have data scientists. They don't really know or understand the platform. I find it interesting sometimes that we expect data scientists to know which GPU is going to be assigned and how many GPUs should actually run on a workload when they obviously don't actually want to have anything to do with this. Yeah. And then similarly, we need to bring people who have knowledge of the platform, SRE engineer, ops engineer, to get to understand the specificity of AI workload. Yeah, so getting all these persona across the life cycle to collaborate and understand their role is also part of our mission. So what we want the white paper to be is, if you are one of these persona, you will basically be able to read this paper and understand where you fit in the AI value chain and what your role in terms of promoting sustainability could be. Let's start with a high-level view of what a sustainable AI platform architecture is. So here, I just want to summarize the big takeaway of this. At the top, you see 2 parts of the life cycle of AI. On the left, you have the model training and the model tuning. The type of problem we are solving here is essentially HPC problems. Ironically, I started my career 20 years ago in HPC domain. Now, I'm working in a totally different job, and I'm doing high HPC on cloud-native technology for AI, solving the same types of problems: scheduling workload, defining priorities, how to build fault tolerance, how to optimize for specific SLO. And SLO are becoming more and more complex. They are not just performance-related. We need to care about power efficiency. We need to care about carbon emissions. We need to care about cost. So as an optimization engineer, all these elements are becoming increasingly more complex to manage. On the right, you see a totally different problem, which is inference. So something very interesting to me is when you see the literature today about AI, it's like everyone wants to do training and tuning. Reality is most business out there, they will spend most of their time and focus and energy on inferencing. If you are not called Facebook or Alibaba or Google, chance is you will not have enough money to train your own language model. So guess what you're going to spend most of your time doing? You are going to take an open source model, hopefully, yeah? And then maybe you'll do a bit of tuning, and then you are going to optimize for inference. Yeah? So this is usually important. Now at the bottom, though, what do we need to care about? As usual, we've got the compute. So here what is very important is, obviously you need to support different type of accelerator. NVIDIA obviously provides a lot of great technology, very advanced capability out there that you can use, but we also see the emergence of new type of accelerator that are usually specialized and give very, very good, rate and capability that are sustainable for very specific type of workload. Next year, you are going to see the emergence, and I mean, it's an easy prediction because I've been working with some of these providers on the hardware side. You are going to see the emergence of hugely specialized chips that are doing specific type of deep, neural network inference, probably 50 or 60% cheaper with lower energy than a traditional general purpose GPU. The cloud provider, if you see AWS as an example, they have two different chips for inference and training. Yeah, so we are going towards a world of specialization, and you need a platform that will be able to easily take this new technology as and when they become available to use their capability. Networking becomes a challenge as well the moment you are going into multi-cluster in particular. Deep trading at scale, guess what? Should I use 64 800 GPU on one single machine for 3 weeks? Or do I want to use 3 different machines connected across an RDMA over converged Ethernet network? Depends. Do you need to go fast? Are you ready to pay the energy premium for the network connectivity? There's no simple answer to this. You'll have to understand the trade-off. And then finishing with the storage. So storage as well, we see a lot of opportunity to improve the way that storage management works, especially caching of model, and especially in the inference workload side. I'll finish with the little thing at the bottom on the right, which unfortunately is small, but is super important, which is observability. Everything that I've discussed so far, if you do not have a way to get telemetry on your platform, you are not going to be able to manage anything or optimize anything. So there's actually a huge amount of work that is going specifically on AI telemetry to understand the performance, the latency of model, but also the span, power, energy, that you have on the workload. We contribute a lot at Red Hat on a project called Kepler, which is a CNCF project, and Kepler basically gives you power monitoring for a GPU. You will see later why this project is hugely beneficial. What type of work are we doing now to make this better, right? To help you as practitioner to optimize your AI platform. There are essentially 3 categories of work. We work on optimizing workload efficiency. So here, the thinking that you should have in mind is, I have a model, and I want to get the same output, but with less energy input. So this is energy efficient framework. How do I make the model smaller? How do I make the model's output as good as my previous model, but reduce the cost of inference? Is an example of it. The second category is resource optimization. Big warning here. In the industry today, the statistics for resource utilization of GPUs are not good. 15–20% utilization is pretty much the average I see, and I speak with a lot of organizations. Yeah? So imagine you buy those hugely expensive GPU, you install them in your data center at the cost of very expensive engineers, trained to do this. And then 80% of the time, they are sitting there waiting for a workload. Not because you don't have anything to run, but because the provisioning is not automated, it's very hard to understand, to have a prediction of who needs the GPUs when. You have to run this multi-tenant, and therefore people are over-provisioning GPU to keep them in case they need them. I could give you 50 different reasons why things are not happening there. It's just the reality, but we have to do better. And the last bit is scalability, right? So if you operate at scale, I don't think that will be the majority of you in the room, but if you operate at scale and you want to go into your own model training or tuning, you will need to start thinking about the problem of usually distributed scaling for AI workload. Right? So we contribute to all this type of technology. All of this is cloud native. So the great news though is, and this I agree with what we discussed in the keynotes, the great news is cloud native is the place where all of this is happening. And it's going to happen more and more on cloud native stack. We know it. OpenAI couldn't train ChatGPT without Kubernetes. Yeah? So that's where we are already. The direction is there. It's set for us. Before I go into some example, I wanted to share a bit the life cycle and a few hotspots. So I mentioned earlier, when you are looking at the AI stack, you have to solve different optimization problems depending on which part of the life cycle you are at. I will just mention the three biggest hotspots. Data management, always totally underestimated. Back in the day, before all this, fad about, AI, we used to call it data science. And data science to me is a better name because in data science there is data. A lot of my friends are so-called data scientists. They've been data scientists way before GenAI. And GenAI hasn't changed this at all. By the way, when I ask them, where do you spend the most of your time on the life cycle, their answer is always the data. 80 to 90% of the time is dealing with sourcing the data, making sure the data can be trusted, fitting the model with the data, validating the model with the data. Oh, I'm ready now, I'm serving the model. Is my problem with data over? It's not, because now I need to monitor the model output to make sure it doesn't deviate from the data. I need to monitor for drift. So data is always going to be at the heart of everything. So there's a lot of things you can do to optimize data workload. A lot of organizations I work with right now, it's not unusual to see 10,000 to 15,000 core of Apache Spark workload just running almost continuously to process data. So that's the first area of optimization. I won't cover it too much today because this one is traditional. It's not really recent. The second part is training. That's where a lot of people focus. And we've got a lot of great projects in CNCF to actually help with this, right? Q for scheduling and orchestration, Kubernetes to basically integrate Kubernetes with Ray cluster. That's been like a huge help for us to start implementing distributed training at scale. But what I want to share with you, and what you see on the right, by the way, is coming from a very good study from our Facebook AI friends. Why Facebook AI paper is interesting is, of course, Facebook is huge in terms of their use of AI, and also the way they have designed their AI internally allows them to have very good statistics to understand the hotspot. To give you an example of this, is Facebook uses Kubernetes inference cluster and Kubernetes training cluster. The inference machine and the configuration of the cluster are usually adapted to the type of workload. So workload never moves in between. Yeah? So thanks to this, they are able to know exactly how much they are spending in terms of resource on all the parts of the life cycle. And something that to me I found usually interesting is even Facebook, which honestly is not probably going to be the type of pattern you see in most enterprise, very clearly says that although we train huge models and constantly retrain them because we had a lot of new data, still 65% of the spend is on inference. Yeah, you can see the little diagram at the top on the fleet, right? The gray bar, 2/3 of the fleet of servers is actually dedicated to inference. Although the majority of Facebook model, they are retuned every week, if not every day, on the new data. So think about it, right? If Facebook, with this amount of retuning, is spending the majority of time on inference and resources, most enterprises that you work with or work for will have an even bigger focus and spend on inference. That's just the reality. Now, that's also a big opportunity as well. The reason is, and this is the other statistic shared in the paper, but I've seen different view of this. Inference provides a huge amount of opportunity to reduce the energy spend and the carbon spend if you start to optimize. So 800, but I've seen Google as well publish 900, 950, is the amount of reduction they managed to get on inference workload by applying efficiency management technique. So that's a good news, right? If the majority of workload is inference, and we can actually reduce that much the power spent on inference, then we can actually, of course, do something good for humanity and climate, but we can also make our bosses happy with the power bill. Yeah? So I'm going to cover now some of the work we are doing specifically on inference and also some of the opportunities we see. And you will see some of these techniques in the white paper I mentioned earlier. So I'm just here doing a deep dive to give you an idea of the type of technique and practices we are looking at. So the graph you see here is kind of how we see inference and the pocket of opportunity we have to make inference better. The things I want to highlight is this, right? The first is, when we look at the total resource we have for inference, there's an opportunity to start thinking about queuing all the requests for inference and start to allocate the inference request to resources and models in an optimized manner. So there is some kind of batching that can be done as well. This batching is more in terms of resource allocation to inference workload. The second type of work what we are doing is, now you have an inference workload. How can I make the energy spend on the start and the memory better? So here there's a lot of work that's happening in the CNCF today to look on model caching. In fact, recently, there were a few new submissions for sandbox project in the CNCF to look at how to use OCI registry and OCI artifacts to share AI models and their component. Why is this important? Imagine I am a serving engine, and instead of going to a relatively inefficient storage layer, I can cache my model directly from an OCI registry. That's going to provide me with a lot of efficiency. That provides me with opportunity to cache and use the cache across multiple inference servers if the same model is used for multiple services. Yeah, so there's a lot of ability we have here to do better with less resources. The last bit I'm going to go slightly more in details is basically a lot of work we are doing to support a very growing trend in AI management in production workload in enterprise, which is people don't want to serve huge 405 billion parameter model. In enterprise today, things that get into production in the Gen AI world, they are actually small models orchestrated across each other and pretty much integrated with the rest of application services. We saw a very good talk this morning about agentic AI. Yeah, this is what is actually going to production today in enterprise. In small agent, they are tuned to meet a very specific mission and output which can be measured. And the good thing with small model is obviously they're small, so they consume less resource. And they provide some opportunities for energy efficiency. So let's see some of this technique. So the way we start in the life cycle of small model is, how do we build a small model to start with? The best small language model out there, they are actually large language model that we have trimmed down. So here are a few key techniques that are being used today on a regular basis to get a small language model that perform almost as well as a large language model, but with a reduced power demand, reduced memory usage. Model pruning is kind of simple. You have a neural network. Let's reduce the nodes that don't really have much to do with the output. Generally, model pruning doesn't give you much challenge with the output quality, and you get some reduction. But the much better technique here is model quantization. What is model quantization? So essentially, with model quantization, we are looking at taking the model weight and reducing the size of their node from really heavy, like 32-bit floating point all the way to 16 or 8-bit. This is the best technique in terms of power reduction of all, but it comes with a challenge. The model output and the quality may be affected. So there's a lot of research going on in this area, but essentially what we find is if you use quantization technique, but they are basically quantization-aware training, so you basically quantize and check the output and tune the output repeatedly, you can get to very small size model that perform really, really closely to a large language model for your specific purpose. And there are projects, open source projects out there that enable the serving of this model very effectively. An example of this is VLLM. So at Red Hat, we work a lot today with VLLM and with VLLM contributor to make sure that we can get some of this quantized model supported in our AI cloud native stack. And that is the reason of this investment in VLLM. I'll finish with this last technique, which is interesting. Knowledge distillation is you are basically using the concept of a trainer model, and you have a small model learning from the large model that is training it for a specific output. That also gives you a reduction in number of model parameters. All these techniques, they result in reduced power consumption, reduced memory consumption for your model. Great news, I've got a small model now. Here comes a new challenge. Let's say you have a small model, but the resource allocation strategy that you have in Kubernetes forces you to use at least one entire GPU. That's an issue, because you are going to have over-provisioning of GPU resources for all your serving. So we want to avoid this. So here the good news is we start to have solutions to actually manage scale of model within model slices and partition. NVIDIA provides us with MIG partitions, right? And recently at KubeCon EU and KubeCon North America, we announced with IBM Research a project called InstaSlice. InstaSlice allows dynamic partitioning. So what it means is as you go and serve model, and this model gets more requirements, you can basically create MIG partitions dynamically on the GPU, and then use them to serve your model within a slice or a couple of slices. Yeah? And we didn't stop there. We started to work on predictive model as well, so using AI to optimize AI. And what we show at KubeCon North America is we can also train model to basically understand the GPUs that are available, the workload footprint as well, and then we'll basically intercept a scheduling to determine what is the best slice that should be used to schedule the model all within the slice, and do this optimization as you go along. Yeah, so there is a huge amount of opportunity here to manage the GPU more efficiently. So that gets us to already a pretty good point. By the way, InstaSlice, we expect it to kind of be market ready Q1 next year, so we are very close. And we are not going to stop there because the idea of InstaSlice is complementary to DRA. So DRA takes care of the overall resource management, but one thing that DRA didn't really cater for is what if you have a very, very small model and it only needs like 1/8 of a GPU? So that's the problem we solve. I'll finish with this. Now, the last technique you have is dynamically managing the power consumption. There's something else you can do with GPU, is you can change the frequency or the power you use of a GPU, and you can declare it. So we recently contributed a project to open source called Climatic with Intel and IBM Research as co-contributor. And what Climatic does is, again, we are using predictive AI and power profile that we define with the GPU maker to understand what is the most optimum frequency at which a GPU can run at inference to maximize the latency output with the least power demand. And the good news with inference workload is there is a way to get 25% improvement in power span with 2-3% impact on the actual latency performance. So that's like a huge domain as well, huge amount of technique available to get more savings. So I'm finished with this presentation. I hope it was informative in terms of some of the direction and the consideration you can have. I just want to finish with this call to action. There are some things you can do now. Let's say you didn't understand everything I've talked about. Well, don't be shy. We have the tag environmental sustainability within the CNCF. I put some QR code there. You can join us. There's a lot of people there who are just discovering sustainability and sustainability for AI. Everybody is very sharing. You can come and learn about it. We'd love to have you around. If you are already an AI platform expert and you'd like to contribute your know-how to the group that is writing the white paper, do scan this QR code. It will bring you to the issue on GitHub where we explain what the white paper is doing. And right now, we are getting more reviewer and contributor on the efficiency technique. Yeah, and the last but not least, I mentioned 2 key projects today where we're still getting more contributor. Kepler is looking at observability for GPU, including performance, power consumption. And then Climatic is doing power capping for accelerator. Thank you for your attention. I hope the session was helpful. I think we've run out of time. I see time is up, big letters here. So if you want to discuss about it or you have questions, just grab me. I'll just be around for a little while. Thank you.